Yes, welcome my YouTube viewers. So for this video, I'm going to present to you about the cholesterol synthesis. So cholesterol synthesis actually involves the very many different steps, but the different steps we compress them and make something that can easily be understood. So the cholesterol is synthesized using acetyl-CoA molecules, and you know how we get acetyl-CoA molecules. It can be like from glycolysis after forming pyruvate. When it enters the mitochondria, it can be converted into acetyl-CoA. Then also during fatty acid synthesis, during fatty acid metabolism, beta oxidation will form acetyl-CoA molecules. So these acetyl-CoA molecules, when they accumulate, they can be converted into cholesterol. So how it happens, we are using these acetyl-CoA molecules. So we shall fuse two acetyl-CoA plus another acetyl-CoA molecule. When we fuse these, we get what we call acetyl-CoA, and this reaction is catalyzed by a thyrase enzyme. So that means during the reaction we have acetyl-CoA plus acetyl-CoA, but we have acetyl-CoA. That means during the reaction there is loss of a coenzyme A. So it is also like CoH. So we have now acetyl-CoA. Now this acetyl-CoA we shall fuse in another molecule of acetyl-CoA. So we shall have acetyl-CoA coming in at this step. Then we shall form HMG-CoA. This HMG can be, it is an abbreviation, but it is the simplest. But if you want, you can say it is 3-hydroxy-3-methylglutaryl-CoA. So during the reaction, that means it is a CoA molecule. That means there is loss of a coenzyme A. And this reaction will be catalyzed by HMG-CoA synthase or synthetase. So this is the enzyme that will catalyze this reaction, and we form our HMG-CoA. So this HMG-CoA, this reaction will be acted on by HMG-CoA reductase enzyme. So this step is the committed step of the reaction. That means when HMG-CoA is acted on by HMG-CoA reductase, it must form mevalonate. And from mevalonate, we can only take it for cholesterol synthesis. But if this HMG-CoA is acted on by HMG-CoA lyase, we shall go for ketone body synthesis. By this time, HMG reductase will commit this reaction to mevalonate, which is synthesis of cholesterol. So it is a reductase enzyme. That means during the process, we utilize a NADPH plus a proton. So that means we release NADP plus. So that is the reaction. This is the committed step of the reaction. And so to regulate, if you want to regulate or to control this cholesterol synthesis, you have to regulate this enzyme HMG-CoA reductase. And so now from mevalonate to form acetyl-CoA, I mean to form cholesterol, there are so many steps, and these steps they always compressed. So the way I do it, I will move directly from this mevalonate and I take you to isopentenyl pyrophosphate. So we come to this molecule. This molecule is abbreviated as IPP. So isopentenyl pyrophosphate. During from mevalonate to isopentenyl pyrophosphate, what will occur? We have different reactions. One, we have 3 phosphorylations. 3 phosphorylations. That means here we are using ATP and forming ADP molecules. Then still after the 3 phosphorylations, we have a decarboxylation reaction. carboxylation reaction. So in the carboxylation reaction, that means there will be loss of a carbon dioxide molecule, because mevalonate is a 6-carbon molecule, and what we are forming is a pentenyl pyrophosphate is a 5-carbon molecule. So there is loss of a carbon molecule in form of carbon dioxide. So that means during this step, if I'm to summarize it, I will say we have 3 ATPs coming in and we form 3 ADPs. Then during the process still we have loss of a carbon dioxide molecule by decarboxylation, and the enzyme taking place here, it is always just, we say, a kinase activity, because there are different kinase enzymes acting at each phosphorylation reaction. So it is a kinase activity. Then now we have our isopentenyl pyrophosphate. So this isopentenyl pyrophosphate, it will be acted on by what we call, it will be IPP, or isopentenyl pyrophosphate isomerase. An isomerase enzyme, that means there is just shift in the arrangement of the carbon atoms, and what we form is called the 3,3 dimethyl aryl pyrophosphate. So this one is abbreviated as DPP. Now these two, this and these ones, they are the ones we call the isoprene units. When they say isoprene units, they are meaning IPP and DPP. So now we have that. So we shall get now, we shall have IPP, or isopentenyl pyrophosphate, and DPP. They refuse together. So if I can now run it from here, I will say we have IPP plus a DPP. Isopentenyl pyrophosphate plus 3,3 dimethyl aryl pyrophosphate. So these ones, they refuse to form what we call geranyl pyrophosphate. Geranyl pyrophosphate. So this is isopentenyl pyrophosphate, this is dimethyl aryl pyrophosphate, but this time we have geranyl pyrophosphate. That means during the reaction there is loss of 2 phosphate molecules. So there is loss of those 2 phosphate molecules, and the enzyme taking catalyzing this reaction, it will be, this is abbreviated as GPP, this geranyl pyrophosphate. So it is always GPP synthase or synthase. So this is the enzyme catalyzing this step. Then now from here, from geranyl pyrophosphate, we shall fuse in a molecule of IPP, isopentenyl pyrophosphate. So that means this is the 10 carbon molecule now, because we fused 5 carbon plus 5 carbon, so we have a 10 carbon molecule. So this time when we fuse in another IPP molecule, we shall form a 15 carbon molecule called the farnesyl pyrophosphate. Farnesyl pyrophosphate, which is abbreviated as FPP. So farnesyl pyrophosphate. That means during the reaction still there is loss of 2 inorganic phosphates, and the enzyme catalyzing this step is called FPP, or farnesyl pyrophosphate synthase. That is the enzyme catalyzing this reaction. So this time we have our 15 carbon molecule. So from this 15 carbon molecule, what we do, we fuse in another molecule of FPP. So that means we get farnesyl pyrophosphate and add another molecule of farnesyl pyrophosphate. And what we form is a 30 carbon molecule called squalene. It is 30 carbon in that we have 15 carbon plus 15 carbons, and so we get squalene, which is 30 carbons. And the enzyme catalyzing the reaction is actually called squalene synthase. It is a squalene synthase. It is the one which is catalyzing this reaction. Now we form our squalene. So we have squaring. Now from this reaction, now this time we shall have so many different reactions which will take place. From squaring to form cholesterol. Cholesterol is a 27 carbon molecule and squaring is 30 carbons. So this time from this step we have to know the differences between squaring and cholesterol. So one, we have to know that squaring is squaring is linear. It is a linear molecule, while cholesterol is a cyclic ring. It has cyclic rings. Then another difference is that squaring has 6 double bonds in its structure, but cholesterol has only 1 double bond in its structure. Then another difference is that cholesterol has a hydroxyl group with carbon atom number 3, but squaring does not have it. So what we shall do now, from squaring we are now forming our cholesterol. But how shall we form it? One, we said squaring has 30 carbons while cholesterol has 27 carbon atoms. That means what we shall have, it will be the carboxylations, which will be 3 of them, because we have to lose 3 carbon molecules in form of carbon dioxide to come to 27 carbon. So we shall have 3 decarboxylation reactions. 3 decarboxylation reactions. Then another thing, we said squaring is straight or it is linear, but cholesterol has cyclic rings. That means we shall have cyclization of the squaring structure to form cholesterol. Another difference, we said squaring has 6 double bonds, but cholesterol has only 1 double bond. That means we shall have 5 reduction reactions. And during these reactions we shall use NAD pH. We shall utilize NAD pH, and so we shall be liberating NAD P. Shall be forming NAD P plus. Then the other difference was which? The other difference was that the cholesterol has a hydroxyl group at carbon atom number 3, but squaring does not have it. That means during the reduction we shall have to hydroxylate. So there will be hydroxylation of this squaring at carbon atom number 3. We shall have to hydroxylate it to make sure that we bring it to cholesterol. So mainly those are the differences, and so that's what we shall do to make sure that we bring squaring into cholesterol. So we have synthesized our cholesterol. This is the pathway which I feel it is actually very easy to understand, and the different books will give different things, but this is what I find actually very tentative to understand, because you get 2 acetyl-CoA molecules, fuse them using a thyrase enzyme, get acetyl-CoA by a thyrase enzyme. Then fuse another acetyl-CoA molecule to the reaction by HMG-CoA synthase, you form HMG-CoA. HMG-CoA reductase will reduce HMG-CoA to mevalonate using NAD pH. Then mevalonate will undergo 3 phosphorylation reactions using ATP from ADP. Then to undergo 1 decarboxylation reaction. It is just 1 decarboxylation reaction to reduce the 6 carbon to 5 carbon isopentane pyrophosphate, IPP. Then IPP isomerase will change IPP into 3,3-dimethyl pyrophosphate. It's not changing, that means it converts some molecules of IPP into DPP, and these are the ones, IPP and DPP, the ones we call isoprene units. So we shall have IPP and DPP condensing by a GPP synthetase to form geranyl pyrophosphate or GPP. There is loss of 2 pyrophosphate molecules, 2 inorganic phosphates. Then geranyl pyrophosphate, which is 10 carbon, we shall fuse in 5 carbon still IPP, and we release 2 phosphate molecules and we form farnesyl pyrophosphate by farnesyl pyrophosphate synthetase. Then from farnesyl pyrophosphate, which is 15 carbon, squaring synthase, we are fusing another FPP molecule and we shall form a 30 carbon squaring. And I said from squaring to cholesterol, we just have to understand the differences between the two. We said squaring is a linear molecule and while cholesterol has cyclic rings. And so during the reaction, we have to cyclize the structure by cyclase enzymes. Then we said squalene has 30 carbons while cholesterol has 27. That means we have to decarboxylate squalene to reduce the 3 carbons and bring it to 27. So we have 3 decarboxylation reactions. Then we said squalene has 6 double bonds in its structure while cholesterol has only 1 double bond. So that means during the reaction we have to reduce. We shall do 5 reduction reactions such we reduce the 6 double bonds to make sure that we remain with only a double bond, 1 double bond that is in cholesterol. Then the other reaction will be, we said cholesterol has a hydroxyl group at carbon atom number 3, but squalene does not have that hydroxyl group. So we shall have to hydroxylate squalene at carbon atom number 3 to come out with our cholesterol, which is 27 carbon molecules. So thank you for watching. Please subscribe for more videos. Thank you.